Here we are. Happy Thursday.
Happy Thursday indeed.
This continues to be one of my favorite parts of my week, Dr. Barth.
Me too.
Go ahead.
No, you do the intro. You do it well.
I'm Eric Seidel.
I'm Adam Barth.
And I guess here we are again for episode 7 of Rubber Duck Engineering. We're going to get even Fourier today.
Yes, so we recap where we are in this project?
Please, bring us up to speed.
Okay, so we're doing sound visualization. So we started out rubbing sticks together and making fire. But we've gotten somewhere now. So we not only can read in a WAV file, we can visualize it in the time domain. And last episode, we applied a Fourier transform, and now we're trying to visualize the sound in the frequency domain. Last week, we had no idea what we were doing, and we drew something on the screen, which I think if Eric shares his screen, the viewers at home can see. But I think that what we showed on screen was basically pretty much garbage. But I have read Wikipedia, the entire thing from cover to cover, and I'm now armed and dangerous with a little bit of knowledge about a Fourier transform.
Somehow I got through many years of math education without dealing with Fourier, or if I did, I stuffed them away in the attic of my brain.
So according to my reading, we made 2 very critical mistakes.
Not surprised. Only 2, though.
The first critical mistake is we took about 1 second of audio and tried to do this frequency analysis on it. Mm-hmm. And apparently a normal amount of audio to take is about 20 milliseconds. So we're only off by a factor of 50.
I see. So our frequencies did, like we were analyzing like whale sounds or something like that. We're expecting to.
Yeah, that's why this chart came out like super complicated, because they're like, okay, you gave us an entire second of like musical audio. There's tons of like frequencies in here. Let me try to show it all to you.
Okay.
The other critical mistake that we made is we just basically chopped out the section of audio and fed it through the Fourier transform, mm-hmm. which means it had really hard edges at the beginning and end. Mm. So if you remember from last episode, when we were taking the example code from the FFT package, they had this snippet about the window, the Han window.
Yeah.
Han window, I don't know how to pronounce it. And we didn't know what to do with that, so we kind of deleted it. Well, it turns out that's important. And what it does is basically, it's like a distribution that's sort of peaks in the middle and falls off to either end. So by the time you get to the end of the snippet of audio that you're dealing with, you've sort of multiplied those values down to 0. And so that creates a smoother shape in the frequency domain, and so you don't get a lot of basically junk in your frequencies coming from the hard edges in the time domain. So
I see.
Yeah.
Okay.
So I think if we make those 2 changes, I think we'll see a dramatic shift in what this picture looks like. Okay. Hopefully for the better.
And what we're seeing on our screen here is I just have our code and the app up on the same screen because I learned how to do that. I also, in the background, upgraded to the latest Flutter dev channel, fixed our hot reload issues that we were having. But that was the extent of my homework. I actually did a bunch of fun programming in Flutter over the weekend, so I kind of use this computer for other things.
You teched up your dev setup. Do you want to demo?
I did.
Do you want to demo the thing you showed me in the green room of this side-by-side code editing thing?
Oh, this is just like living the Flutter dream, which you normally get when you run the iOS simulator. You run it on your like iOS or Android device, but we're using this, sort of experimental desktop background. But I figured out how to split tile the screen on my Mac here, and then you're just doing the standard sort of Flutter demo of you change a color, and you hit save, and then you're sad because it didn't work. I don't know.
Ooh, green.
I do like that the editor shows me these things. Anyways, hot reload was working.
All right, we should try actually programming it.
Maybe I busted it.
Okay, so I think the easiest thing to do is we should just switch from being basically 1 second to being 20 milliseconds.
Okay, so I think that was down. If I put some of these window parts away, that was just the number of samples that we were grabbing.
Yeah, so we're expressing how much audio we want in terms of sample counts, which is a little awkward.
Yeah, it was a little weird.
So if I remember correctly, our audio file was basically 8 kilohertz.
Well, this was the FFT wanted a power of 2 samples?
That's correct. I also learned about that on Wikipedia. Turns out FFT can handle an arbitrary number of samples. It's just the library that we're using is using a particular algorithm that works by basically recursively subdividing, and so it only works on a power of 2.
I see. Okay, well, so sticking with that, does that mean we need to write a function that takes time and translates it to the number of samples and then finds the nearest power of 2? Or like, are we just going to grab one?
I mean, we could do that, but we could also just like hard code it. Like, I think in principle we should, you should read from the WAV file in time instead of in sample count. But I don't think it's worth dealing with that. So
yeah, I don't think we need to refactor that now.
Yeah, so we just need to do a bunch of like math in our heads, or maybe using a calculator. So if we want 20 milliseconds, and the sample rate is at 8 kilohertz. So if we wanted if we wanted 1 millisecond, that would be 8 samples. So if we wanted 10 milliseconds, that would be 80 samples. And if we wanted 20 milliseconds, that would be 160 samples. I think if I did that correctly. And so now we need to find a power of 2 that's close to 160.
Okay. I don't know the powers of 2 off the top of my head.
So our choices are 128 or 256.
That would make sense. So let's try 128. Okay. Power of 2 to make. This is like package. Okay.
I suspect we could find a fancier FFT package that could take.
Yeah. All right. So it's. Oh, there comes our hot reload back again. I don't know why it was busted. Okay, so now we're down to a lot fewer samples. We still have this like mirroring effect.
Yeah. So the mirroring effect I learned about also. So the mirroring effect is because we have an entirely our input to the FFT is all real numbers. It's no complex numbers, and apparently that means that the one half of the FFT will be a complex conjugate of the other half. And then because we're taking the norm, so we're basically squaring it, it ends up being symmetric. Okay. So I suspect that what we're actually supposed to do in the visualization is throw away half of it. Okay. But I think we can worry about that in a second.
Okay. You wanted to apply the window.
Yes. So let's apply the window.
I'm searching for where we do this.
So I read the docs for the FFT package.
Okay.
So there's an object called the window, which we want to construct, and we want to pass in a window type of. We could either use Hamming or Han. It doesn't really matter, but the one in the example was Han, so I was going to go with that.
Where would I find those docs? Do I need a full?
I can just So if you just go to the pub.dev and go to the FFT package.
Dev FFT. So when we tried this before,
so their sample code. Compile. Their sample code is not legit. But if you go to their API reference,
okay,
in the FFT library, there's a class called window. And so you construct this window by saying what type of window you want. In our case, Han or whatever. And then there's a method on it called apply, which takes in a list of numbers and gives you back a list of numbers. So you basically just need to call that function before we hand it to the FFT. Okay,
so we do. Does it modify the list?
Well, there are no docs. It just. Get factors, multiply lists. I assume because it returns a list that it doesn't modify the numbers, that it gives you back a new list with the window applied. I think, by the way this is designed is we shouldn't be creating a new window object every time. We should be basically using a saved one because it's caching the factors that it's going to multiply all the numbers by.
Like a globally saved one? Let's see, frequencies we create all the time, I think.
Yeah, I just think we should have a final, global final. Oh yeah, final stack. Yeah.
I don't think it's final window. This is like shared window. It's equal to window.
There's no dot. You just passed window type dot pawn or whatever.
Han. Let's do it, Han.
Wikipedia said something funny. It said some people call it the Hanning window because it sounds similar to the Hamming window. I really apologize if I'm mispronouncing it. I just read about it on Wikipedia. I did not actually listen to a human being say the word.
I do wonder sometimes, given how often it is that we just have basically no idea what we're doing, just enough to be dangerous, maybe we need to rename the podcast.
Well, that's why the duck is rubber, so it doesn't hurt anybody.
So when we start pelting our knowledge at people. Okay. So we need our shared window, and we want shared window dot apply with one fewer p samples dot channels, I think it was.
So what's going on here is, remember we have a list of lists because we have the left and right channels.
Oh yeah.
So we need to actually do this in the map.
You are correct.
So we can't use our super awesome like tear off constructor map.
We did get a little,
which is incredibly beautiful, but like it doesn't scale to what we need here.
Okay, let's fix this here. So this is going to be list of complex channel. This is like channel data.
I think this is actually just a list of num. Like we haven't applied the transform yet, so it hasn't gotten complex on us.
Okay, and now we need to do our window. We could just do var. Whoa, hello, what happened? Typing is so hard. Okay, and then we're gonna FFT transform this sucker.
I kind of wonder if we should cache the FFT object. I don't know if it has any internal state or anything. But
so this probably is actually, we just need this. This doesn't compile because I screwed up something somewhere.
Do you want me to try? We need to move this sample. Oh, you're doing it. Yeah. Go for it.
I'm doing?
You got it. And then instead of samples channels, you want channel data.
Is this correct? Yeah. You think we should cache the FFT?
It seems the way this library is designed, like I wouldn't be surprised if there's...
I have no idea what twiddles are.
I think it's just a thing that it caches to go faster. Like there's a lot of... This algorithm seems to be like extremely well studied.
Okay. It would appear, yes, that we want static. This may all totally blow up in our face, by the way.
It might. But we'll never know if we don't try.
I just mean, like, it's always a little odd when you like have global caches, because then you can have like things bleed between. Wasn't like a fast fire department or file descriptor. Oh, I see you making a private here.
I think I'm making private. Just
oh man,
was it just, that problem?
Was it hurting your soul? Okay,
it was. Oh, see, look. Oh, that's very interesting. Look, if you remember what this looked like a second ago, the like little peaks at the edges were taller, and now they've sort of like thinned out. Because I think this is like the very beginning of the file when it's quiet.
I'm so amused that we just hit save, and it just, like, I was getting all ready to switch to the next one, and here it is. You already can see it. Okay.
Do you want to press
so
play?
Whoa!
Yeah. It's feeling a little bit more like what it's supposed to do, right? I think.
Well, I don't know. Like, what am I seeing? What does it mean to be 0. Like,
So, okay, this is supposed to tell you the power that's in each frequency. So, like,
so there's lots of high frequency stuff. Is that what this is?
well, maybe we need like a simpler test wave function to a test wave file to check ourselves.
I just like it's spending all this time way up here, which I don't know what that means. Whoa, that was like when they start playing the guitar or whatever, it gets more interesting. I mean, this data looks like data that I have like seen coming out from somebody's like recording setup.
Do you want to try 256 instead of 128 just as an experiment to see? I'm just curious if it looks significantly different.
Well, I also, isn't this then drawing 128 numbers? And isn't that like the wrong, because we need to bucket these, right?
We could bucket them.
But with only 128 samples, like, is this 128 separate parts? I just still don't, maybe I needed to read the Wikipedia article, 256. I don't really understand what I'm seeing. All right, so here's the 256. So it is as though like it has higher resolution. I still don't understand why it's like way up here always.
My guess is that's some kind of like garbage issue. Like,
I see.
Because like theoretically, we're supposed to be looking at a periodic function as the input, but at the beginning and end, right? It's not a perfectly periodic function, and so there's a sort of discontinuity when you go from the end of the window to the beginning. And
so
the window function is trying to counteract for that.
To go back to your supposition of, hey, what if we had a simpler wave file? Like, what if we just had a wave file that played, A440? What would that look like? What would you expect it to look like?
So I would expect like a pure sinusoid to look like a single spike on this graph. But I would expect like like if you're playing the violin and just playing a pure note on the violin, I would expect to see a main spike and then littler spikes for each harmonic. And then the shape of those spikes, then that's what it means to sound like a violin, is how the harmonics distribute.
So say we had a pure note. So we're seeing, when we do 256 samples, isn't then this also showing us, I mean, only 128 of this is actual data. But it feels weird to me that we're mapping 256 samples from the time domain into 256 sections of the frequency domain. Like, does that smell weird to you too?
So this is the difference between the discrete Fourier transform and the like pure mathematical continuous one.
Okay.
So if you think about the discrete Fourier transform, we're saying, okay, here's an interval from 0 to 1, and you have some resolution of what you're sampling for. If you tried to look at frequencies that were higher than your sample rate, then you're just going to get garbage, right? So it can only give you as much detail as that. And there was something about in the Wikipedia articles about the Nyquist rate, which in the word Nyquist in my mind is associated with this kind of problem. And I didn't fully read those sections of the articles, and so I don't know. There may be some correction that we're supposed to apply there that may be why we're getting these big things at the edge. But
our sample rate is 8,000 hertz.
Yeah, so normal audio files are like 44.1 kilohertz.
I see.
And so this file, I don't know why, we just happen to download it off the internet, right? We don't know where we got it. So one thing we could try, I think is a good idea, is to try a simpler wave file and see if we can understand what the plot is telling us.
Okay. So do you happen to have one handy?
I don't, but I think we just look for like, you said A440 or something, or A?
Yeah, A440 is like a tuning frequency.
Yeah, so maybe that's like an A440 wave file.
I wouldn't be surprised. Here's
I mean,
an OGG.
I found one on GitHub called 440.wave.
Does it come with a license?
Well, a lot of stuff I get has a license. This one, I don't particularly see a license for it. Do you want to show your web browser?
Oh, we may not be able to check it in then. I guess, but we could play with it and find a different one then when we're off camera. But sure, send me a link and I can download it. We can try loading it in.
Let's see. I put it in the private chat.
Sounds like a plan.
I don't know what it is. I could try to listen to it locally. Let's see.
Oh, okay. Fascinating.
I can't hear it. Were you able to hear it?
It should just sound like a tone, like kind of thing.
That's what I was hoping for, but Chrome wasn't able to play it for me.
Yeah, Chrome isn't able to play it for me either. So okay, let's keep searching. Maybe I should do something else with our viewers while we search away here.
Okay.
So let's see. If I look at this, it bothers me that it runs off the edge here. So I could add a clip. It's a little weird that it's pinned to the top.
Oh, yeah, you should totally fix that. It's supposed to be flipped over. And do you also want to cut it off so it's not mirrored, so you only see the...
Mm-hmm. Okay, so let's look at that. So if I go down to... Okay. Let's see what our painter is. So remember, we used a custom painter. We made a copy for the time painter, and we made a copy for the, I think, frequency painter. Yeah. So this would be the frequency painter that we're working through, and we want to only paint half our samples. Okay, so if we, like a simple thing that might just work is if we just do this. Do the right thing? Okay, so there we're successfully painting half of them, but not the full distance. Okay, so that's going to be in our add to path function. I'm not sure if that's the right fix, but I'm trying that for the moment. If we go back up to our add to path function, which I define within, here we go. We're doing the width divided by sample count. Okay, so the right solution, right fix here is to change our sample count down to do this. Samples we get from FFT are mirrored around the y-axis. We only need to show half of them. Okay, let's see what that did. There we go. So that's better. I still don't understand what all this garbage down here is. Maybe this is what you were talking about before, about when things are...
I don't know, like if you're, I think those are showing you like frequencies that are really close to your sample rate. And so I think that's, I think it's not really real data.
Okay, I can believe that. So what's the scale here? I know you're typing away and you're Google searching here, but is the scale like, is it like like logarithmic of sorts? Like, it's not like a linear scale, obviously. There's some sort of like the further you get away from 0, it must move in non-even steps. Here again, I should have read the Wikipedia article so I could speak more intelligently. I lost you to the Google hole. It's fine.
I'm just making sure the licensing is proper on the sound.
I see. So you can check it in. Great. Adam and I have worked many years in open source software, and you become a little sensitized to these things, but getting your licenses right. Because cleaning it up can be a big pain.
It's just, I just view it as a matter of respect. Like, this person has done the work to put a bunch of nice sound files on their website, and I just want to like respect the work that they put in.
Okay. Okay. So, and then we talked about flipping this because this really should be from the bottom. So I suspect the easy way to do that. So I can either do that with a transform applied, or I can just subtract the y from the height. Subtracting the y is a little more hacky, but probably way easier. So if I do y, why is this height divided by 2 for the y range?
That I think is a thing that came from the time domain where we're going above and below, and it may be incorrect for the frequency.
I see. Yeah, that feels like it. All right, so y range, let's do. Okay, so that expands it. I don't know if that's correct or not, but if we take and we do y range minus y, that should probably do the right thing. There we go. And do we need to flip the x as well? I don't actually know if this should be 0, of like this high end or the low end.
I think you want it flipped. I think the place where it hits 0 on the right is the 0 frequency.
Okay, another easy way to flip it would be to.
I think you want to take the other half.
Yeah, exactly.
Yeah.
So this is just channel count. We start at and channel count times 2. Oh, I must have screwed up.
Sample count, I think, rather than channel count.
Ah, you're right. Yeah, I probably hit an NPE there. Yeah. Okay, so okay. This is a little hacky. Really, what I should do is I should just slice it out instead of like trying to adjust later. So let's see if I can remember how to slice Dart arrays, Dart lists. It's like just sublist. If I do model dot but we come in multiple samples, which is a little gnarly. Okay, so maybe this is easier. Okay, so if I took this and I just do sample count, a little hacky here, probably wouldn't pass code review, but that should do it. Nope.
Did something. I think it's okay to have it like this, I think, for now. So if you go to the GitHub repository and pull, there's now a new example sound file. I think you should check this in. This seems like a big improvement over what we had.
I don't remember why I changed it to green or what I changed to green here.
I think we were playing around with the colors too.
Oh, that's why it wasn't hot reloading. So I was changing the wrong one. I was changing the time one. This is not going to hot reload when you're changing code that you're not running. Okay. Let's see, does this look right? Okay. And so what we did? Make FFT work more. It's such a terrible commit message. Okay.
So if you look in the examples, so this is not, I didn't find a pure tone. Instead, this is a C note on some sort of electric piano.
I love, by the way, that you you gave us a third-party directory with sourcing.
It just habits, like you know.
Well, no, it's actually really, because one of the things, I lose context. I mean, do a few other things in my week besides talk to you on a Thursday nights. No offense, Adam. But I tend to lose context, so I have to write everything down. And so I like that it's written down so we have some idea where we got it from.
I also read what the person wrote on the license, and basically what they're looking for is acknowledgement, which is a common thing to want in a license.
Sure.
Just say, you know, hey, we got this from this source. Like, give credit where credit is due.
Okay, so since we're parsing a new WAV file, we're going to have to back up, and because what I expect is going to happen is that our WAV parser is just going to blow up, right? Because we had all these assumptions in the WAV parser about the one true WAV file.
It was a highly tuned parsing this exact WAV file.
A little overfit to our model or whatever. All right, so we run it though. Hello interwebs.
I assume that was debugging something that we put in our code. Either that or our program has grown a sense of humor.
Very possible. Okay, so hello interwebs, we can remove that. Riff.
Yeah.
Okay, we have a higher sample rate.
Yep. Yeah, this is the normal sample rate.
Okay. So this, I don't see any exceptions being thrown.
Mm-hmm. So I think we should basically look at this using the time visualizer to see what the waveform looks like. I'm hoping it's going to be a way simpler waveform than what we were looking at before.
Okay, so now we have to go back to our... So what we really should do is we should make this toggleable, because this is not going to be the last time we want to do this.
Yeah, sure. Why don't you add a little switch somewhere that switches back and forth?
Where should I put it?
The easy thing is just to put it in that same bar that has the play and the pause button. But I think it's better if it were like floating on top of the graph, but whatever.
Like a... I mean, I could just add like a... what's it called? Floating action button or whatever? I could add a fab. It's a little lame. I could put it up here in the app bar. It's not entirely...
Oh, yeah, put it in the app bar. That's a good idea.
It's not entirely correct, but...
It's actually not bad in material design. If you put it on the right, it's common to have little toggles on the right in the app bar. Like,
what is that called?
Actions, I think. Actions, yeah.
Okay. Actions. This is going to then need to be... You just want like a clickable button kind of thing?
I just have a toggle.
Remember what it's called? Well, not complete.
Oh, I think it's called a switch.
Toggle button.
Switch. Switch. Yeah.
Okay. Yeah, I have to go read docs because it's been a while for. Oh, okay, this thing. Yeah. I actually remember you writing this.
We're staring at each pixel, trying to make it the perfect shade of whatever color it was.
I remember specifically, because I worked at Apple for a long time, so I know lots of people still there. And I just remember sending your Cupertino one, and some of the bugs to the individuals who had worked on that same code. and we were amused at the different set of bugs that the two controls had, or the total lack of bugs, of course. That
The code was perfect. 0 bugs, 0 rendering artifacts. I believe it takes a Boolean value and then has an onChanged function.
You just have this filed away in your okay, value and onChanged. Yes. Okay. Okay. So where are we going to save? Can we then pass this down to the wave player?
Yeah, I think so. I think we basically want like a for now, like
yeah.
What do I call it? Use time.
Sure.
I mean, it really should be an enum, right? Because like we're gonna have other visualizers.
Well, which means this really shouldn't be. Well, but that's fine. Yeah. All right. Bool, you get use time. you can implement this however you want. Here's your little getter.
Oh, really? You're really gonna do this to me?
What do you mean? I'm really gonna do this to you? If you're gonna, like, I want to abstract away from our little lame switch. Like, okay, so then if we're not gonna do a switch. Then we're gonna do a pop-up, right? If you're gonna have more than one, then we can't just have a little switch. Well, either it's a bool and it's a switch, or it's an enum and it's something else. Except then if it's an enum, oh my god, then we have to write all the boilerplate that Dart enums require us to do. Oh, you're doing it.
It's gonna be okay. I can handle it.
I got decision paralysis, and you just started typing.
I agree that it's slightly ugly. Oh.
And how are you going to invert this to neon changed?
I don't have to invert it. It'll just I'm just gonna type it out.
You're just going to rewrite this code completely next week when we switch to having multiple.
That's fine. But in the meantime, we're unblocked.
Okay.
I can spell frequency, right?
We're
player.
We're missing an extra comma here to make this guy splat out here.
Yep. Where's our wave player? Wave player. Oops.
Wave player, play me a wave. Oh, I think we've overloaded the poor analyzer.
We've hurt his brain.
Well, it doesn't seem to be saving after my change. Okay, let's pull up this problems. Expected to find, oh, what? You need semicolons? There we go. Okay, it's a lot happier now. Visualizer type.
Yeah,
oh, I see you're adding that right now.
Can you scroll up to the wave player part? Thank you.
Are you not able to see? Does like my scroll affect you?
Your scroll does affect me. It's always wants to scroll your cursor on screen for me.
Huh. That's fascinating. I actually can't see where you are.
That's because I'm typing in the wrong class.
It's okay. I did that earlier tonight.
I got slightly distracted. Okay, let's. Whoa. Okay, that's cool. All right, can you move your cursor up?
Where would you like it to be, sir?
I would like your cursor to be on line 242.
242.
If you
are right.
Perfect. Thank you.
That's what I am tonight. I'm the cursor scroller. They keep me around. It's past my bedtime. It's okay.
We got to pass it through to the sample plot too. There's this funny thing that you end up doing in Flutter sometimes. We end up plumbing information through, and there's all these cool like flex, react, something.
Well, yeah, this is what like the provider package and all those do, where they let you, Flutter also has this concept of. All
right, would you be willing to scroll up to line 197?
Yes, sir.
Thank you so much.
How was my scrolling tonight? Please don't forget to tip your scroller. Yeah, Flutter has this like where it will like look up things that are up tree from you, and there's a there's a nice package provider that'll do that too. You can provide things down the tree for some state management. We're not using it here, but we totally could. But yeah, in Flutter, if you need to expose your state down the tree, you got to pass it down or find some way to get it down.
It's kind of nice in some ways, like you can see the explicit data flow, but it does get repetitive if you're passing a lot of stuff.
What are we doing here? Oh, I see. We're doing our switch.
Sorry, we're doing the actual
Yep.
internalized way. It's just the UI at the beginning.
Yep.
Okay, I think I typed it all in. The analyzer hates it, so I assume that you're going to fix it and make it perfect.
That's me. I do analyzer fixes and scrolling. Value time painter cannot be returned. Why not? You're a widget. Oh, you're a custom painter. Did you mean for this to be a custom painter?
I think it could be widget. I think I need to basically move the sample reading up there.
Because you might. Well, yeah. I mean, or this thing gets past the. Because eventually you're going to want to get past the model.
I need to change the return widget. Like it's a widget is a base class of custom painter. It should be okay. Yeah, so I could have made this function take the model. Maybe that would be a better way of doing it.
Yeah, that seems like a reasonable thing. Somebody's job is to build the model, and somebody else's job is to hand the model off to the API, right?
Yeah, I guess in some sense we want to like generalize the ability to make a visualizer, so you can make any kind of visualizer you want. In which case, all right. Why is it unhappy now?
Time painter cannot be returned. This is a custom painter, which is not a widget.
Okay, I think we want it to be a widget because I think we want, like, in general, if we wanted to have crazy visual.
Oh, totally, yeah. They might not use a custom painter. They might use some crazy 3D thing. Yeah, so.
What's the name of the, is it called Painter? Is that the name of it?
Might have to look at how it was called before, but that sounds reasonable. Does the custom paint do anything here other than like take this other custom painter object?
I think there are other parameters you could give to it.
See, so okay. Expected to find. Oh, we must have made a copy paste error. Children. I see this. Okay. I believe we're. Whoa, hello. Build function return null. Don't you dare.
Oh, I think you need to try toggling the switch. I think we need to initialize.
We're in sad panda land.
Right, we didn't actually pick a default visualizer type.
Oh yeah.
If you go to line 311.
That's fine. I just use the analyzer. You just need someone to click on the latest analyzer error because that does the scrolling for them. It's like our job as engineers, right, is to code ourselves out of a job. Whoa, hello.
Okay, that's cool.
So this is, I see. So we're in time series, and this is our, we're like moving between the channels.
Well, keep in mind, this is now 44.1 kilohertz instead of 8 kilohertz. And we're also looking only at 200 and, I guess we're still looking at 8,000 samples here. So we may want to look at, oh no, we're still only looking at, right, we still only have a tiny number of samples, 250 samples. So if we want to look at a second, we should look at 4,000. I think we're running up against a sort of limitation of our data structures where we are using the same number of samples for our time visualizer and our frequency visualizer, even though they probably want to have way different ones.
Okay.
But we can just try it for now. Like we just multiply this by, I don't know, 100. Okay. 108.
Okay.
Too much. Back off. 24. What? 24 is not a power of 2? That's really wrong.
I mean 16 or 8. Okay. So now what are we looking at here? All right,
Hit play. Let's see.
I also love, by the way, that this was all hot reload. So like we were still seeked midway through the file.
So okay, so what I'm seeing here is a few pure tones.
Why does this necessarily look pure tone to you? I'm seeing a lot of change in amplitude. Have you listened to this?
I have listened to it. I wish we could play through the strain bit.
Yeah, we need to figure out how to set that up.
Do you see every once in a while something goes by that's a nice pure tone? Like that? So just scrub around a little bit. Yeah, like that.
Why does that strike you as a pure tone?
All right, maybe it's not pure. It's
Well,
just loud.
I'm not actually sure what a pure tone, how I would distinguish a pure tone.
Why don't you scroll to a place that has a big one of those, and then we'll go look at the frequency domain by toggling the switch.
If it worked. No. Let's see. Do we have debug console? I think it must be a power of 2? No. Is this not a power of 2?
I think it's power 2. I'm really to believe my toggle thing is wrong. Oh, I didn't call set state because I forgot that too.
Oh, down in your toggle. I should scroll so that. Hold on, let your scroller catch up with you.
So I just dropped that in at set state. When the inner tube's unclog, you'll be able to see it.
Okay.
Now try your toggle. Maybe it'll work now.
It's still a sad panda. Okay, let's clear this so that it like starts tracking again. Okay, I want to try a hot restart just for giggles. That doesn't seem right. If it restarted, it should have lost state. There we go. Okay. Whoa. What are we seeing? Okay. That looks more like a regular tone.
Can you flip the switch? Are we in the...
That's the time domain.
Oh, I wonder if we were still looking at the other wave file.
Oh, we totally could have been, because that's not going to get changed by hot reload.
Yeah. There we go. This looks more like what I heard.
Okay. So yeah, so it starts out as a loud. It starts loud and gets softer.
Yeah, it's like pressing on the key, like boom.
Yeah, and it looks like a pure tone. Ish.
It's not a pure tone, but at least it's way more regular than the other one.
Yeah. Okay. So now when we flip into the frequency domain.
Okay.
Okay, so we see overtones, right? These should be cascading overtones, but this is still not nearly as clean or as pure as I would expect. Maybe because we should put the samples down?
Yeah, let's bring the samples down.
And we can fix our model. Are you doing it or am I doing it?
Go for it.
It's just 256.
Well, keep in mind that we're at 44 kilohertz now. So so 20 milliseconds.
Oh, don't make me write the function. This is the kind of thing that I do, like when I'm programming. Even if we, whenever I do a hack like this, I'll just write the function that says, "Hey, for this amount of time, I want you to do, I want you to return me the number of samples." And then in that function, I will just write return 128, and I'll write the comment. Because then when I hit this kind of bug, then I like. The scaffolding is all there. The expectations are all correct in the code.
Yeah, I think that the generalization of that is not to hold too much in your head and just try to write it down on the page, whatever you were thinking.
No, totally.
Yeah, so I feel like we've hit this pain point enough times. We probably should refactor to actually do the math. But we don't have to do it in the last 11 minutes of the show. Yeah,
I think we should figure out how we're gonna. Because again, this is my brain's already shutting down. This being far past my bedtime, but okay, I think we should think about where we want to like bring us into land for the evening. I wish we had gotten a little further about, like, I'd like to see a, oh. I just don't understand why this is, see, and now we can't really see the tones. I think something is just isn't quite working yet.
Yeah. I see we still have our print statement that's printing out every frame, giant numbers.
I don't know why we were doing that in that. Okay, so our print statement's gone.
Oh, it's way faster now.
Yeah. Turns out getting a lock to write to standard out is expensive. Okay. I just don't trust what I'm seeing here. But I don't have a lot of intuition. Like, this sort of looks right? Like this.
Yeah.
This strikes me as good. But I don't understand why it's way off the charts up here.
Mm-hmm. Those are good questions.
Also, like, where is... So the overtone should be going higher in frequency. So, okay. So this is the low end of the frequency.
Right. I would expect to see a spike at the... Because if you go back to the time, if you toggle back to time...
Yeah.
Oh, look at that. It's not enough. You see? We can't even see a whole wave yet.
I see.
So why don't you try... Why don't you multiply?
I love that we can toggle. It's so cool.
Yeah, I'm glad we added the toggle. That
It just, like, I've never been able to do this in any other sound editing, sound editing program that I didn't, go out and, plow my own fields and grow my own wheat just to bake my one loaf of bread. Okay.
Do you want to try a number here like 4096? Just
why don't we do like POW 2 to the...
But then we can't show off how cool we are for knowing all the powers of 2.
9? We were at 8 before, right? Our 8 is 256? Because that's one byte?
Yeah, sure.
This is what Google is for. Okay.
Is POW...
POW must not be it. Oh, you know what? We're at Dart. Everything's on the object. But it's to POW. It's mod POW.
Mod POW. Slow down.
It's totally on the object, though, because it always is, but I don't remember what it's called. Oh, don't make me. POW function Dart.
Oh, it's in the math library.
Really? Okay. Okay. I was wrong. I sit corrected. But we have the math library in here, don't we?
We had it for a brief moment, and then we realized we didn't use it. But now apparently we want it.
It's amazing to me that we've done as much, math. How? Okay, where was it? Samples. Power of 2. There we go. Okay. POW 2 9. I would expect that to have changed. Right? Because we just should have made it twice as big. So this should have gotten half as wide.
Ooh, try 10.
It's almost as though like the 9 didn't update. Yeah, somehow the 9 didn't hot reload didn't update. So 9 now does an entire sample.
Not quite enough. So I think we should try maybe even 11.
Oh, we're taking it.
We took it to 11.
We took it to 11. Okay.
Okay, so what does that look like in frequency land?
This is so cool. What does this mean?
Doesn't quite seem right, does it?
Whoa.
Well, we can see the power drop off, so we got that going for us.
It's gorgeous. I also don't understand why it goes, like, talking about going to 11, like, why does this go way past our expected domain? Like, what were we... is this our normalized function? That's the time painter. I want the frequency painter. Frequency painter. It must go to 32-bit integers?
Oh, yeah. I don't know. Try it. I did learn that the FFT is linear. So if you multiply the inputs by 10, the outputs will be multiplied by 10.
I'm just trying to, what is the number that I want to divide by here? So like
2 times that, yeah. You may need parentheses.
Oh, details. Order of operations. Okay. I should have done it.
I don't know if the... Yeah, I'm really curious how big that spike goes. Like,
yeah, that's where I was trying to understand.
I don't know, divide by another 2. Or multiply by another...
Well, I didn't see it. Oh, okay. It is adjusting.
It's just really, really big.
Where are we going? Like,
we're going to space.
like,
try again. I don't know. Try a 16.
So what is this? This was 16-bit signed integer, so this might be a 32-bit unsigned?
I don't know if it really corresponds that way. Like, if you have a really pure tone, like, it'll just be like an infinite spike at one point.
Oh, because this is showing... I don't understand. What is this graph showing me? Like, I guess one of the things I'm asking is, like, so we see it go back to 0. Now that we see it on camera, per se, like, maybe this looks reasonable, right?
Yeah, I wonder if we were just looking at the tail, and that's why it was looking like garbage before.
Well, we're also looking so way out into the tail.
Yeah, what if you shrink that window down? Like, what if we just zoom in on the left side of this graph?
Well, so what is the x?
The x should be frequencies.
That goes to, but what is the distance between values of x? Hertz? Like, is this at x440? Whatever this was. Come on, I thought you read all of Wikipedia last night. Aren't you now the FFT?
I my way this far through the show. Like,
it's okay. We're both tired, or I'm tired at least.
It's not about being tired. I just don't know. But I think we were onto something. Like, what if we only looked at the beginning part? Like, what if we only looked at the first 10th of this? And
yeah, I just don't know if this makes any.
I don't know. I'm just.
I mean, we can do that. We're really getting into hack territory here. I want to go to the frequency painter, which I'm at, and I want to change.
Yeah, just take the sample count and divide it by 10.
I don't know if that'll do what you want it to do, because remember, we were already doing this weird thing where we started at the... Oh, we stopped doing that. Oh, I see. We didn't ever do that. Okay. Divided by, sure, 20. So now we're just looking at the very beginning. Like, that looks...
It looks like what I want it to look like.
Yeah.
I don't know
what the noise around 0 here is.
The noise... Okay, so this I actually do remember. So the 0 in the frequency domain is the amount of direct current that you're getting. So if you were to average your samples across your entire range, if they average out to 0, then that would be 0. But if they average out above 0, then that'll come through at the 0 coefficient in the frequency domain.
So what I'm hearing you say is that there's still post-processing we have to do for the FFT result before we expect to just plot it like this.
I think what we're looking at now looks reasonable. I kind of wonder if we switch back to the other wave file, what it looks like.
To the time
we don't
machine.
have a toggle. We don't have a toggle for that. But.
Well, that's the kind of thing I think we need to build next time, because I actually think we don't want to be reading these as files off of my hard drive. What was this one called?
This is the C, like middle C.
But rather, instead of these being files off my hard drive, they could even just be links into like HTTP links into GitHub or whatever.
Mm-hmm.
And then this also just then would start working. Well, it would be closer to working in Flutter Web or on your machine, things like that.
Mm-hmm.
Okay, let's see. It was like example.
Well, I guess look here.
Wave.
Wave, yeah.
And this is guitar. It's going to yell at me for not using the variable, but that's fine. All right, so now
I think you don't.
We have to hot restart because we're literally doing this in our main. We're holding it wrong here. We're certainly holding it hacky. Okay. So this is presumably time again.
This is time again. Yeah. So.
Yeah. And we switch into frequency.
I mean, this is looking like what I kind of think these things should look like, right?
Yeah. As I said, I need to read Wikipedia. Like, I still don't.
Yeah, I think we're not quite holding it exactly right, but I think we're holding it a lot better than we were an hour ago.
Wow. I'm sold. I'm really happy.
You can see the beat. Can't you see the beat? Dun, 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 dun.
I haven't listened to the wave file enough, but I can see a beat.
There's a beat going on.
Yeah, I like this. It always amazes me both how little and how much we get done in 1 hour. So before we close up, do you have any good thoughts to share with our viewers tonight? Anything exciting you learned this week? I'm putting you on the spot. I didn't actually come with anything in particular.
I learned that I did some homework, but probably not enough. And
I really like that we're finding our rhythm here, both literally and figuratively. And yeah, I'm definitely enjoying this, Adam. I really appreciate you making the time. Yeah. Any more before we say sayonara?
So I think maybe next week I'd like to get to the point where we have a plugin interface.
Okay.
And if people out there are watching and they get excited and want to try to write a plugin, like I think if you tune in next week, we'll hopefully be able to set that up. And then, then if you send in a visualization, we may show it on the show.
Yeah, I think that'd be cool. We'll come up with an API next week, and we can hear from our viewers. So,
yeah. See you next week.
See you next week.